All right, this video is going to be on Newton's third law. This is the final part of chapter 3, the final one of Newton's laws to learn about. So please have your guided notes out and following along here. Newton's third law, let's start with the definition of what it is. Okay, you're supposed to write down the definition. And here it is. Newton's third law states that for every action, there is an equal and opposite reaction. For every action, there is an equal and opposite reaction. Raise your hand if you've heard about this force, or this one of Newton's laws before. Okay. Newton's third law, yeah, it's pretty common. We hear it a lot. But what we're going to do now is actually talk about it and explain what it means. Both in terms of conceptually what it means, but also we're going to put numbers to it and we're going to solve problems quantitatively. Okay, forces. Forces always occur in pairs. So in Newton's third law, when it says an action and reaction, that's what an action and a reaction are. They're forces. Forces. So we're going to draw free body diagrams with forces in it and identify Newton's third law. Okay, in other words, the force of A on B is equal in magnitude and opposite in direction of the force of B on A. So in physics textbooks, you'll see it written like this: the force that A puts on B is equal to the negative force that B puts on A. Remember, they're equal, but they're opposite. How do we show the opposite direction in physics? With the negative sign. So that's where that negative sign comes from, showing direction. So the equation that I'd really like you to remember and write down is this one right here. Okay? Here's how you would say it. The force that A puts on B is equal to the negative force that B puts on A. Okay, so Newton's third law. They're equal forces, but they're in opposite directions. Okay. Okay, I've got some pictures up here. It says in each of the following pictures, each of them demonstrate Newton's third law. Identify the action and reaction pairs. So I want you to come up with the action and the reaction pairs. Let's start with the baseball bat and ball up here. What would the action pair be? The bat hitting the ball. Okay? So is there a force that the bat puts on this ball? Sure. And hopefully that force is making the ball go out into the outfield somewhere, right? Okay, now let's talk about the reaction pair. What's the reaction pair of this? The ball is hitting the bat. Okay? What could we say about the magnitude of those forces? Which one's greater? Does the bat put more force on the ball? Or does the ball put more force on the bat? Or are they equal? Think about Newton's third law. Has an equal but opposite reaction. So that's what everyone thinks, is that this bat is somehow putting more force on the ball than the ball is on the bat, because the ball goes farther, right? But here's how you think about it. The bat is going to hit the ball and it's going to have a force there. Well, the ball has to have the same amount of force on the bat. But why does the ball travel so much farther? Why does it accelerate so much more?
Has less mass.
Good. Ryland's got it. The mass of this ball compared to the bat and the batter, isn't it very small? So the mass is very small. So that means the acceleration is going to be huge compared to the bat. Okay. Stick with me. Let's go through a few more. Let's go to this runner down here now. Where's the action and reaction pairs to this runner? Yeah, it's with the feet, right? Isn't there a force that the foot puts on the ground and it's going back? Right? When you run, you're pushing backwards. So if that's the force that the foot puts on the ground, what's the reaction pair? Yeah, it's the force that the earth puts on your foot. How would you describe their magnitudes? Which one's bigger? Or are they the same? They're equal. They're just opposite directions. Now, let me ask you this. Why do you accelerate, but the earth doesn't? Think about it in terms of mass. Yeah, the earth's mass is way larger than your mass. But imagine that you were standing on, now imagine you were standing on a very small, let's do a log roll in the water. Now when you run, what happens? The log turns. How come you don't go forward? Or let's just say it's on the ground. Why does the log roll and you don't? Because the mass is different, right? So it always comes back to mass, and figuring out the acceleration will come into mass, and I'll show you how to do that in a few problems. Okay, but just realize that the force that the foot puts on the ground is equal to the force that the ground puts on the foot. They're just in opposite directions. Okay, rockets work the same way. The space shuttle here. What's the action pair? The force that what is putting on what? Isn't the rocket fuel kind of propelling out these rockets and down onto the air? Right?
Yes.
Well, if Newton's third law is true, what's making the rocket go up?
The air pushing.
The force that the air puts on the rocket. Why does the space shuttle move up? Well, it's got less mass, so it accelerates a lot more. Okay? This is kind of a funny one to think about. This bus is going to hit this little bug right here. This is a bug. Okay? What's the action force going to be when that happens?
Bug smashes.
Bug hits window. Okay, so is there a force that the bug puts on the windshield? Okay, now what's the reaction pair? There's going to be a force that the windshield puts on the bug. Now, which one is going to change acceleration more? The bug. Why? It has way less mass than a bus. And so the bug is going to feel the same force, but it changes its motion a lot more than the bus will because its mass is way less. Okay, so anyway, just a good practice there, identifying the action and reaction pairs. Remember, forces always occur in pairs. There's always pairs. All right, I've got a practice problem here, number 12. Let's do it. It says a physics textbook with the weight of 10 newtons is sitting on a desk. What is the force that the desk is applying to the book? Draw a free body diagram and label each force. Okay, so here is my book. Okay. For this free body diagram, I'm going to draw the desk just to better illustrate what's going on here. Okay, it said the weight of this book was what? 10 newtons. So weight is equal to 10 newtons. Now, is this book moving up and down? No. So there must be a force that's going up and it must be balanced. What do we call that force? The normal force. And we've talked about that so far. What can you say about the magnitude of that normal force? It's the same, so it's got to be 10 newtons. Now, is that Newton's third law? Is there a force that the book puts on the desk? Yeah, it's called weight. What is the force called that the desk puts on the book? The normal force. Now, Newton's third law says they're equal but opposite. How come this isn't a negative 10 newtons? Because doesn't this arrow already show direction?
Yeah.
Yeah. And in physics, when you go down, what is it? It's negative. So we don't need to put a negative because we already have the arrow there. But that's an example of Newton's third law. Equal but opposite forces acting on that book. Okay, this one is not in the book. It's not in your guided notes. But let's talk about it because it's kind of a commonly used example for Newton's third law. It says, how is shooting a shotgun related to Newton's third law? Also, why does a rifle have less kick than a shotgun? Let me draw a picture and see if I can illustrate this a little more. Okay, so here's the gun, the shotgun. Whoops. Okay. So there's my shotgun. Whatever. I can't draw. How does that relate to Newton's third law? Yeah, there's a recoil, right? Is there a force that the I guess, what would you say? What's the action and reaction pairs here?
So the gunpowder gun.
Is there a force that the gun puts on your shoulder? Okay. And is there a force that the shoulder is putting on the gun? Yeah. Okay. So, but I wanted to get a little bit deeper than that. What's causing the force initially? Isn't there a little, in the bullet, isn't there a casing for a shotgun shell that looks kind of like this? And there's a little primer here. When you pull the trigger, this makes the gunpowder explode, right? So that gunpowder exploding causes these little BBs to come out. Well, there's equal but opposite forces here. When that forces it out, the gun to the right in this case, the gun is also feeling the same force to the left. And that's what kicks you, right? When you pull the trigger. It also wanted you to say, how does that compare to a rifle? Which one kicks more if you've done both? Which one kicks more? Shotgun. How come? Well, with the rifle bullet, isn't it much smaller casing? So here's the casing. It's much smaller casing, and there's less force here going out, and that means the opposite force coming back, the kick, is going to be much smaller. Anyway, hopefully that kind of makes sense with Newton's third law. Okay, let's go to practice problem number 13. This one you do have in your guided notes. Let's talk about it. Okay, it says a sumo wrestler has a wrestling match with you. The sumo wrestler has a mass of 150 kgs and accelerates towards you at 5 meters per second squared. Guys, think about that. Is that realistic?
He's coming at you fast.
5 meters is like the width of this room. Is a sumo wrestler going to be able to do that in 1 second?
Oh yeah. Go.
No. That's okay.
He's flying.
It's not realistic, but I'm using it just to kind of illustrate my point here. Okay? And you have the mass of only 50 kg. So I like to draw a picture. What is it asking here first? What force of impact does the sumo wrestler have with you? All right, I like to draw a picture. Here's the sumo wrestler. Okay? He's 150 kgs. Right? And here's you. And you are 50 kgs. How does your mass compare to his?
1/3.
You're 1/3 the mass of his. Okay, and also he's accelerating at you at 5 meters per second squared, which is an incredible speed. He's not going to be able to do that in real life, but I'm just using it to illustrate this point. Okay, now let's answer question number 1. What force of impact does the sumo wrestler have with you? How do we find force, guys? Force is equal to what? MA. Which one of Newton's laws is this? Second law. Force is equal to, what's the mass that this sumo wrestler has? 150. Okay, what's the acceleration? 5. What's 150 times 5? 750. So 750, and it's a force, so what are my units? Newtons. Okay? That's how much force he's going to hit you with. Okay? Yeah, that's a large force. Number 2, what force upon impact do you have with the sumo wrestler? So if he hits you on this free body diagram up here with 750 newtons, what are you going to hit him with? Yeah, you're going to hit him with the same force, 750, but it's going the opposite direction. You can either say negative 750 or 750 to the left. Okay, Newton's third law, equal but opposite. Number 3, how much do you accelerate due to the impact of the wrestler? Okay. Again, it's asking about acceleration. So which one of these equations, which one of Newton's laws could we use? Second law, force net is equal to ma. What force do you experience? 750 newtons. Whoops, 750. What's your mass? 50. And we don't know the acceleration of u. How can we solve that though? Divide both sides by 50. So acceleration of u is equal to what? What is it? 15. 15 what? What's the units? Meters per second squared. Okay. Now 15 meters is like the length of this room from front to back in 1 second. Is that realistic? No. But the reason I did it is to kind of illustrate this point. How come he's only accelerating at 5? How come you're accelerating 3 times more than that at 15?
Because he's 3 times heavier than you.
Because his mass is 3 times more than your mass. That's how it works. If you got less mass, you're going to feel more acceleration when you hit, right? You see this all the time. With sports, there's a lot of sports analogies you can make here. And we'll do a demonstration at the end of class with air track over there, and I'll show you. Okay, number 4, if the action statement is the sumo wrestler exerts a force on you, what is the reaction statement?
You exert force on the sumo.
Yes, you exert a force on the sumo wrestler. All right, that's it for this chapter. What I've got is some slides that kind of summarize what we've talked about. This is a very important chapter talking about Newton's laws of motion. Okay, so let's summarize it. Who can tell me Newton's first law?
Weight equals mg. Oh, wait.
No, what did it say? An object at rest stays at rest. Object in motion stays in motion unless it's acted upon by a net force. Okay, so yeah, motion stays in motion, rest stays at rest unless there's a net force. If there's a net force, what's going to happen? It's going to accelerate, and that's Newton's second law. So force equals ma is Newton's second law. And we just talked about the third law, but for every action there's an equal but opposite reaction. And forces always occur in pairs. Okay? So I've got some slides here to summarize that. You're supposed to fill out this table on your guided notes. Let me give you a second to do that. This table is summarizing Newton's first law. If the object is at rest, what can you say about the forces acting on that object? Well, they have to be balanced. There's no net force. That's why it's at rest. But here's the one that students kind of forget about. So put a little star by 2. If an object is moving at constant velocity, what can you say about its forces? They're balanced. There's not a net force. If there's a net force, what's it going to do? It's going to accelerate. So then there's unbalanced forces. That's when you do see a net force. So yeah, put a little star by 2. Students always forget that one. If you're moving at constant velocity, that tells you that the forces are balanced. Okay. Let's talk about Newton's second law, which says if there is a net force, can you figure out how much the object is going to accelerate? Sure. And Newton's second law is basically this equation, put into words. Force net is equal to ma, the most famous equation in physics. So when you get to a problem and it's talking about forces and it wants you to find acceleration, this is your go-to equation. Okay, and then finally, Newton's third law. Forces always occur in pairs. And here's our equation that we're going to use. The force that A puts on B is equal to the negative force that B puts on A. For every action, there's an equal and opposite reaction. Okay, very good. That's Newton's laws. We're going to use them for the rest of this physics course. And hopefully that makes more sense. Okay? We've learned Newton's third law, and there is a worksheet in the student workbook called Newton's third law worksheet. So please go to Newton's third law worksheet in your student workbook and get that done now. And hopefully this helped.
Okay.